Today we'll begin looking at a new unit, starting off with looking at higher order derivatives, including velocity and acceleration. We will begin looking at our higher order derivatives since they are derivatives of derivatives, which we already know from Unit 2 of what a derivative is. So if we're looking at f double prime of x is an example of a higher order derivative. It is the rate of change of the rate of change. We use these derivatives to study rates of change. So looking at velocity and acceleration as motion on a straight line. An object that moves along a straight line with its position determined by a function of time s at t has a velocity of v at t, which is just equal to our s prime of t. So the derivative of s at t. And an acceleration of a of t, which is our s double prime of t at time t. So s at t is our displacement, and s prime at t, which is equal to our v at t, is our velocity. Alright, and when looking at velocity, we need to make sure that we're looking at the direction, okay, because direction does matter. Because when talking about speed, which is the absolute value of our v at t, this will always be positive. And our s double prime of t is equal to our a at t, which is equal to our acceleration, which is just our rate of change of velocity. So the units of velocity are displacement divided by time. The most common units for velocity are meters per second. The units of acceleration divided by time squared. The most common units for acceleration are meters per second, or meters per second squared, or meters per second squared. So since we are assuming that the motion is along the number line, it follows that when the object is moving to the right or up at time t, our velocity, so our v at t, is going to be greater than 0. And when the object is moving to the left or down, our time t, our velocity, is going to be less than 0. And if our velocity is equal to 0, the object is stationary at time t, so therefore it changes direction of movement. So now let's discuss about accelerating and decelerating. The object is accelerating when both v at t, so our velocity, and our a at t, our acceleration, are positive or both negative. This is when v at t times our a at t is positive. So therefore, when looking at this, our s prime of x would be positive and our s double prime would also be positive, or both would be negative. And when we're talking about deceleration, they are going to be different signs. So that is when you multiply your v at t, so your velocity times your a at t, which is your acceleration, this will be negative. So therefore, when we're discussing our s prime, if our s prime was negative, our s double prime would be positive, or vice versa. So now let's look at our first example here. So please note we're not going to actually use this chart here, alright? I unfortunately couldn't take it out since it's a PDF, so just ignore that for now. So in example 1, an object moving along a straight line is represented by the graph of s at t. So in part A, we want to look at when the object is moving to the right, left, and at rest. And then what we want to do is we want to look at when the object is accelerating and decelerating. Now, when we're talking about accelerating and decelerating, this isn't a major concept when we're talking about calculus. This is something you would talk more about in physics. So to begin here, let's just look at our part A at rest. So when is this function going to be at rest? Well, we know our function is going to be at rest when our tangent is horizontal. So if we look at this graph here, we can see that we would have a horizontal tangent at these two positions. So our first one is when our t value is equal to 2. So at rest is when t is equal to 2, and our other one is when t is equal to 6. Now, from above, we talked about when our function moves right and left. So what I would like you to think about when I mean right and left, when we talk about right, we're meaning going away. So our object is moving away from us and moving to the right. Now, when we are talking about left, we are talking about when the object is moving to the left, but it's coming back to us, coming back to the origin. So when our function is moving right, this is when our time is less than 2. All right? And also, so you can see that by just looking at our graph here. Okay? So it's increasing, all right? So therefore it's moving to the right. It's going away from the origin. And also you can see that when after t is greater than 6, it's also again moving away from the origin. So also when t is less than 6. But if we look at this in terms of, looking at when we're going to the left, all right, so coming back to the origin, it's after its rest point. Okay, so therefore it's going to be between our two rest points in this case. So from 2 to 6. Okay, so remember, when it's going right, it's going away from us, it's going away from the origin. When it's left, it's coming back to us, coming back to the origin. All right, next when we're talking about accelerating and decelerating, again, this isn't going to be something that we're going to get into too much detail about, but when our function is accelerating, is between 2 is less than t, which is less than 4. Now, the reason for us stopping at 4 and saying that it's accelerating, because our object is still accelerating as it comes back to the origin. It's just that it's accelerating. When it gets to around 4, it's going to have to start slowing down so that when it gets to our point here at 6, it can slow down and turn and go in the opposite direction. So our accelerating is going to be between 2 and 4, and also when t is greater than 6. Okay? And then decelerating, which we have talked about a little bit, when it needs to slow down. All right, we know it's going to be between 4 and 6, as I showed you above, and also when t is less than 2. So we will now begin looking at example 2. A fly ball is hit vertically upward. The position function s at t in meters of the ball is s at t equals negative 5t squared plus 30t plus 1, where t is in seconds. So just to get a visual of that, we can look at our function here. We know that our y-intercept would be at 1, since that is our constant value there. So we know that we would have this parabola form here. So in part A, we want to find the maximum height reached by the ball. So to find our max height, this occurs when our velocity is equal to 0. So what we need to do is we need to solve for our velocity. Now remember that our velocity is just equal to our position function when we take the derivative of that. So when we take the derivative of that, it's going to be negative 10t plus 30. And since we know our max height occurs when our velocity is equal to 0, we can now set that equal to 0 so that we're able to solve for our t value. So we bring that 10t over to our left side, divide both sides by 10, we get that t is equal to 3. So now that we know that our t value is equal to 3, so our time is at 3 seconds, we can now take that value and put it into our position function. So s at 3 will be equal to negative 5 times 3 squared plus 30 times 3 plus 1. When we expand and simplify, we get that it's equal to 46 meters. So therefore, the max height is 46 meters. So now for part B. Part B, it says find the velocity of the ball when it is caught 1 meter above the ground. So we're talking about the velocity here when it's 1 meter above the ground. So first things first, we need to actually look at our s at t is equal to 1. So we want to look at our position function to find out, well, what are the values when it's caught? Okay, we know from looking at our graph here that we start at 1 meter, so that ball starts at 1 meter. But looking at this, it starts here, and it continues, all right, and somewhere over here, we know that the ball is going to be caught. So we need to find out when that happens. So we set our position function equal to 1, and then we go ahead and solve. So we have 0 is equal to negative 5t squared plus 30t. And when we solve this, we can factor out a negative 5t, and we're left with t minus 6. So obviously that happens when t is equal to 0 or when t is equal to 6. So I know it's going to be when t is equal to 6 seconds that the ball's caught. So now that I know that the ball's caught at 6 seconds, and in B it's asking for the velocity when the ball is caught. So now we take our velocity, so our v, we're going to put in 6 for our time to find the velocity at 6 seconds. And when we do that, we're going to get negative 30 meters per second. So therefore, the velocity when the ball is caught at 1 meter is negative 30 meters per squared. Now remember, velocity can be positive or negative. Velocity is just going to tell us what direction it is going in. So we know that it's coming back to us, it's moving left. Whereas if we were talking about speed, speed will always be the absolute value of velocity. So now example 3, the position of an object moving on a line is given by our position function s at t equals 6t squared minus t cubed, where t is greater than or equal to 0, where s is in meters and t is in seconds. So in part A, we want to find the object's velocity and acceleration at t equals 2. Obviously 2 seconds here. So remember, when we're taking our velocity, it's just going to be the derivative of our position function. So let's do A here together. So our velocity will be equal to 12t minus 3t squared. And if we're talking about our acceleration, remember, is just equal to the double prime of t, which is just the prime, or the derivative, of our velocity. So that will just be equal to 12 minus 6t. And if we want to look at that when t is equal to 2, our velocity would be equal, just by subbing in 2 here, we would get that our velocity is equal to 12 meters per second. And talking about our acceleration at 2 seconds, we have 12 minus 6 times 2, which would give us 0. So therefore, we have a constant rate of 12 meters per second at 2 seconds here. So then in B, at what time is the object at rest? So when we're talking about an object being at rest, we're going to look at our velocity. Okay, and we know that our velocity will be equal to 0 when our object is at rest. If we were thinking about that as our graph, you could think about that as when we have a horizontal tangent. So we set our velocity equal to 0, so 0 equals 12t minus 3t squared. We can go ahead and solve, so factor out a 3t, and we're left with 4 minus t. So t is equal to 0, or t is equal to 4. So therefore, the object is at rest at t equals 0 seconds and t equals 4 seconds. Now in part C, in which direction is the object moving at t equals 5 seconds? So we're talking about what direction is it moving. So let's look at our velocity. So we look at our velocity at 5 seconds. Sub in our 5 there, and we get that is equal to negative 15. So therefore, we know that the object is moving left. Okay, so it's coming back to us. It's coming back to the origin. So now in part D, when is the object moving in a positive direction? So when we're looking at the object and moving in a positive direction, we're going to look at the velocity. And we're going to look at the velocity between certain values. So we're going to look at it between its rest points, so 0 and 4, and we're also going to look at it when our time is equal to 2 seconds, because we have a constant rate there. So if we're talking about our velocity, we know that our velocity would be negative when it's less than 0. Between 0 and 2, it's going to be positive. Between 2 and 4, we'll have a positive velocity. And after 4, we know it's going to be negative, which we just solved for when looking at C. So therefore, we know that it's moving positive. So positive or to the right. When t is between 2 and 4. Now in part E, it's asked us to find when does the object return to its initial position. So it's gone on its course and it's come back to its initial position. So we know that at the initial position, okay, is going to be at the same value when t is equal to 0. So we can find what that position is because we know if it's the initial position, it's coming back and it's being that same value that was started as. So we find s at 0 is just going to be equal to 0. So therefore at 0 meters, sorry. So we sub in 0 equals our 6t squared minus t cubed to find out when it's going to get back to that initial position, because remember our s at t is our position function. So this will be equal to t squared times 6 minus t, so t equals 0 or t equals 6. So therefore it returns at t equals 6 seconds. And now looking at F, we want to look at when the object is accelerating and decelerating. So for F, we can talk about, again, our velocity and our acceleration between the points 0, 2, and 4. So we discussed already in D that our velocity will be between 0 and 2 positive, between 2 and 4 positive, and 4 onwards it will be negative. Now when talking about our acceleration, if you look back at our acceleration function there, it's 12 minus 6t, so you can just put in values that are between 0 and 2. So if you put in a value between 0 and 2, such as 1, you'll get that your acceleration is positive. If you put in a value between 2 and 4, such as 3, you'll get that your acceleration is negative. And if you put in, say, 5, again, you'll get that it's negative. So when talking about accelerating, and you look at your values here, when we discuss accelerating on the first page, we know that this is going to happen then between 0 and 2, and when t is greater than 4, because we have to have both our velocity and our accelerations both to be positive or both to be negative, and our decelerating is therefore between 2 and 4. So now in example 4, we want to discuss the motion of an object moving on a horizontal line if its position is given by s at t equals t squared minus 10t, where t is between 0 and 12, and s is in meters and t is in seconds. We want to include the initial velocity, our final velocity, and any acceleration in our discussion. So we're given our function s at t equals t squared minus 10t. So I know that I want to discuss my initial velocity and my final velocity. So let's find our velocity. So remember, our velocity is just a derivative of our position function. So our velocity is just equal to 2t minus 10. So since we are given a range here between 0 and 12, I know my initial. So if we're finding our initial is when our time is 0, so we would have this being equal to negative 10 meters per second. And our final, since we're given a range, we know is at 12 seconds, which is equal to 14 meters per second. So that's just discussing our initial and our final velocities. So now let's look at what about when our velocity is equal to 0, so when it's at rest. So it's always good to know when it's at rest because that is our turning point. So we have 0 is equal to our 2t minus 10t. We can go ahead and solve for our t value here. So we have that our t value is 5. So therefore the object is at rest at t equals 5 seconds. So we can also discuss our acceleration. So our s double prime of t is, remember, is equal to our acceleration, so which is just the derivative of our velocity. So our acceleration is going to be equal to 2 meters per second squared. This is just going to be a constant. So it's our acceleration is a constant on our whole position graph here. So if we sum this all up here, when we're talking about our velocity and our acceleration, and we'll talk about acceleration and deceleration. So our velocity for less than 5, so between 0 and 5 would be negative. Okay, we can just sub in a value, say 1, and you'll get that it's going to be a negative value, but greater than 5, our velocity is going to be positive. And then using our acceleration function here, for less than 5, it's going to be positive, and greater than, it's also going to be positive. So since our acceleration is constant, it's always increased, or it's always staying at a constant, all right? It's not going to be a negative acceleration anywhere. But talking about acceleration versus decelerating, so remember, decelerating is more like it's just slowing down. It's got to slow down as it gets to that point. So by looking at this, my accelerating is between 5 and 12, and my decelerating is between 0 and 5. Sorry about that, I wrote my greater than and less than signs wrong there. So a t should be less than, there we go. So that is example 4.